Hello and welcome. My name is Aaron Lopez. I'm a performance analyst. With me, my friend and colleague, Jeff Deweese, who is a solution architect. We both work in professional services at Esri, and today we're going to be talking about tuning and scaling ArcGIS Enterprise. This session will cover strategies and techniques for optimizing and getting the most out of your enterprise deployment. We'll be starting by giving you an overview of our agenda today. For instance, we'll talk about ArcGIS Enterprise, key components such as ArcGIS Server, portal for ArcGIS. Then we'll talk about service fundamentals, authoring, optimizing services, and things to keep in mind. After that, we'll cover service models, different types of services to choose from, their behaviors, as well as optimizing a site for one or potentially many services. We'll follow that with a discussion on web map tuning, how you can optimize system resources through your services, and how to take advantage of this strategy through web maps. Jeff will then talk about system scaling, different architectures for scaling ArcGIS Enterprise, and follow that with a talk on workload separation, strategies for separating loads to optimize scalability. So ArcGIS Enterprise. ArcGIS Enterprise consists of 4 components that make the base deployment. Portal for ArcGIS. This is the component that hosts services and applications. Now there's not much tuning that can be done based on your amount of content, but backup models, for example, are certainly worth discussing. ArcGIS Server. This is the engine behind the scenes that draws maps and performs analysis. And this component is probably the most impacted from poorly tuned services. ArcGIS Data Store. This provides relational data store for use with hosted feature services, and we'll talk about some things to keep in mind with that. Lastly, here we have the web adapter, and the web adapter is an optional component that can be added to deployments for certain functionality, and we'll talk about things you can do with that. So the base deployment with ArcGIS Enterprise is the starting point, and you can certainly expand from there, either by adding GIS server roles or scaling out your existing role. For example, GIS server, you can add multiple machines to expand that role, or if you're taking the route of expanding your capability, you can add an image server, geo event server, business analyst server. But before you start scaling your deployment, consider providing good infrastructure like stable storage, ample hardware resources. These should be one of the first steps you make when tuning any deployment. Service fundamentals. So getting the most out of your services starts with map authoring. And some things to keep in mind with this is that desktop maps don't always scale for the web. They're built for a different purpose. So as you publish your maps for the web, consider that it is being put in an environment for multiple users. So as we look at some strategies that you can use for your authoring, consider scale dependencies and generalizations. Remove unneeded layers, hide fields you're not using. We can't expect users to turn off layers in the application. They may not know which ones they need or don't need, but as authors, we do. So we can optimize our map, put our best foot forward, and only present the data that we want the users to use. Along these same lines, it's a good idea to limit what the user can do with your service. For example, if you don't need KML as a capability, don't enable it. If you're presenting a feature service for viewing, don't enable editing. And ArcGIS Enterprise gives you fine-grained control over how you can edit your feature services. So as you publish publish these your data into services, this is something to keep in mind. So general data considerations. Well, a good take on this is to match the feature class to the accuracy of your data. So if your data is only in the meter, there's no need for the millimeter resolution. There's no need for that extra accuracy. Indexing the file in enterprise geodatabases appropriately. For enterprise geodatabases, you have another take, and that's maintaining statistics. This can help with your query plan to ensure that your queries are optimal. And it's a good recommendation to use the spatial type for your RDBMS, such as the ST geometry or the native spatial type. The spatial type is this can help influence how your data is indexed, how fast spatial extent queries can be made and returned. So it plays a big part. So enterprise geodatabases. This is a topic that deserves, rightfully so, its own session. So we're only going to spend a slide discussing at a high level the enterprise geodatabase with respect to tuning. Enterprise geodatabase data is fast, provided that you keep your statistics up to date and your indexes are set on the fields that you're querying in your queries. It provides current data availability. So if you're editing it, you can see that data as the changes are being made. And it's required for traditional versioning or branch versioning. Branch versioning, this is the more modern way of doing versioning, typically with Pro and Enterprise. And this is a design that's built for today's users, many concurrent users, and the web. It's a simpler table structure using time-based design, no more adds and delete tables, no state tree, lineages, much simpler. The other end of this spectrum would be file-based data, for example, file geodatabases. Also fast. Helps if you keep them closer to your server, for example, ArcGIS server. Works great with static data, data that's not being edited or requires frequent updating. You can also get a benefit by making a performance benefit by making your file geodatabase read-only, as then the system doesn't have to worry about locks. It doesn't have to worry about preserving that accuracy. So that's a nice practice to follow, is enabling or making your file geodatabases read-only. Compared to shapefiles, file geodatabases are faster, delivers better performance and scalability, greater storage limits. Service models. So as we discuss service models that are available to you, it's important to provide a life cycle, a discussion on the life cycle for a traditional, dynamic, dedicated service. And this is important to discuss because this process, these concepts are important, as a deployment becomes busy with lots of concurrent requests. So we would start up at the top as the user trying to consume a GIS service. We make a request, goes in through the web adapter, which in turn forwards the request to our GIS server. The request is then picked up by the appropriate handler, REST. So OGC tile, for example. That in turn contacts the service and asks the service for an available ArcSoc process to start working on the request. If it's free, great. The system can immediately begin working on that request, and that data is sent back to the user. However, if it is really busy, there is no free ArcSoc process, then the user will wait And that may or may not be an issue. If it is really, really busy and the users are waiting an extraordinarily long time, their request will time out. And then a message is sent back to the user saying that their request could not be fulfilled. And we bring this up because, for each of these instances, these ArcSoc instances, they can only handle one request at a time. So it's this idea that we want to, make this known, make this practice known that ArcSocs, having free ArcSocs, that's something an admin needs to keep in mind. So we have three service models. What we had just discussed, that was the traditional dedicated life cycle, but there are others. So we have the dedicated traditional model. This is ArcSoc based. You have fine-grained control on tuning your service settings with the traditional model. You also have hosted. This is not ArcSoc based. This utilizes the relational data store of ArcGIS Enterprise. And third here, you have the shared instance pool. This is relatively new. This provides a group of instances that are always available for various services, whatever you put into it. This is also ArcSoc based. And something to keep in mind as we talk about ArcSoc and ArcSoc processes, all ArcSoc based services, their requests will have a traditional ArcSoc server log entry. And we'll bring this up later and discuss why that can be important for an administrator to understand. So dedicated services. Let's take a deeper dive into dedicated services. So we said you have a more fine-grained control over them. You have probably two settings that are most impacted, the day-to-day options for tuning, and that's your minimum and maximum ArcSoc instance settings. Your minimum setting, that's your memory utilization at rest when the system is idle. This minimum defines what will always be consumed, always be running. The maximum setting, on the other hand, that defines the concurrent requests to be serviced, how many you will allow to be running at a maximum at peak demand. If it's not set high enough, well, users wait. So it's not the end of the world if they wait a little bit, but what we're concerned about is users waiting too long. We're always concerned about the user experience. We want it to be great. So this is where we have to juggle this minimum and maximum understanding based on what users are asking for. So a common administrator goal is to find that right balance between a minimum and maximum setting for a dedicated service. Users' patterns, they change all the time. And what could be done for the previous year or the last quarter, well, now your company has, your institution has a new focus. So now we have new services with a new application. So that's something that you need to keep in mind. It's always changing. That said, there are tools that can help you with this that's always changing. Since the demand and the popularity of services are in a constant state of flux, it can be a lot for an administrator to keep up on. And there are some tools that can help. One is System Log Parser, which is a free utility you can download. And there are ArcGIS Server statistics available with ArcGIS Server that can help provide you this information of quantifying your GIS, quantifying your services, the popularity, and the performance. So with respect to ArcGIS Manager, ArcGIS Server Manager, what does it look like, the minimum and maximum instance settings? So here we can see a screenshot from Manager where we have a minimum of 1 and 2. That's the default. And that's important to note. That 2 may not be enough if your service is very, very popular. You may want to increase that accordingly. Now, if you have a site, as we had talked about at the beginning, you might expand your GIS capability. So say you have 3 servers for ArcGIS Server. Your maximum then would be a total of 6 instances for any one service, because that's 2 times 3. You have 3 servers. Your maximum is multiplied by the number of machines. So it, while 1 and 2 may not be popular, may not be enough for very popular services, as you expand out, you may have additional resources that it's taking advantage of. For dedicated services, you also have timeouts, which can be very handy to adjust where appropriate. If you need more time for the service to run, or if you are trying to conserve memory, you can adjust your maximum time an instance can be kept running to free up memory. So you have a lot of ability to fine-tune, as we said, dedicated service. Caching services, worth mentioning, do not use an ArcSoc process. So if you have tile cache as a service, you can set the setting to a maximum of 1 to conserve memory, and you would be just fine. So dedicated services, some things to keep in mind as you adjust your minimum and maximum is to not over-allocate your resources. Your maximum is defining how many instances can be running at any one time concurrently, but each of these instances does take up memory, so it's important not to add and add and add, to the moon. You want to be strategic at how you set your instance settings. Concurrent users, though, is not the same as concurrent requests. So if you have an office of 5 people, it's very unlikely that you're always going to have 5 ArcSocs running for that service. Even if you had 5 users on the system at any one time, users aren't continuously issuing requests to your deployment. Many times they're making a request and then analyzing, digesting the actual response that came back to them. So that's important to keep in mind. So determining, whether or not your site has, what type of services your site has, is another challenge of admins. So it can come down to, 3 scenarios: having many services with low popularity, or a few services that are in high demand. Alternatively, you can have a mixture of both. You have a good group of services that aren't requested very frequently, so you still want to keep them around, but you have 3 popular services that are driving the new application for your company, and so you want to ensure that they have enough resources to get the job done. So for the services that have low to moderate popularity, historically, a popular option was to set their minimum value to 0, right? Sounds good. You have no memory at rest, and when requests come in for the seldomly used service, they spin up, and that can be okay, but we recommend you use the newer shared service type instead, and we'll discuss here shortly why. So, hosted services. Before we get into the benefits of shared, it's worth discussing hosted services. As we said earlier, they don't use an ArcSoc process. They use a Java process that's threaded and highly scalable. So this can support a lot of requests. It's auto-managing, as it's managed by ArcGIS Server, and as the requests come in, it spins up what's needed, and they close down appropriately when the requests go away. Win-win. So you have the hosted services, these requests. If you're interested in profiling their performance, an easy way to get that information is through your web adapter access logs. Another characteristic of hosted services is that they typically favor client-side rendering, where the data is returned as JSON or PDF. This type of service gets its data from the ArcGIS data store, relational data store, for example. So shared services, as we were saying, this is a big deal. It's new, introduced a short while ago at ArcGIS Server 10.7. We definitely think it's a game changer. It utilizes this shared instance pool, which is like where it's a group. It can house a group of services that you want to publish that aren't necessarily the most popular, but still critical. You want to keep these services available and keep them around, but you're concerned about resource utilization. If that's you, if that sounds like you, then shared services are a great candidate. Some things to keep in mind that requires ArcGIS Pro to publish a shared service, and not all service types are available. For example, geoprocessing and utility network. As we look a little more at shared services from the point of view of ArcGIS Server Manager, this screen highlights an important setting worth discussing. So when you install ArcGIS Server, it auto-detects the number of CPUs, and the shared service capability takes advantage of this and sets this value accordingly. So in this case, we had an ArcGIS Server on a 10 CPU machine, and our default value for the number of shared instances is 10. And that's great. So we have a lot of services that we can publish here, and overall this is going to help reduce the memory footprint, and it is a better option than the min equals 0 because we're always on and we're minimizing the startup cost. And the startup cost for some services, I mean, it varies greatly, of course, but it can be anywhere from a few seconds to maybe even tens of seconds. So we can have 10 instances for any services that we throw into this grouping that are always available, can be serviced right away, which is great. Great. It really helps reduce hardware resource utilization, and helps make your system run more optimally. So another example is comparing how shared services look with respect to a dedicated service. So in our top table here, we have a system running several services with a minimum of 0 and a max of 2. And if all of these services were running, we'd have 15 instances on the system consuming memory. But we can only go up to 2 concurrent Arc SOCs for the majority of these services. However, under the shared pool model, we are only using a maximum of 7 running instances, and our memory savings is essentially half in this example, but we can still support a higher number of services in this grouping, and there's no startup penalty that we have to wait for these services, as we have 4 instances always on, ready to service the requests as they come in. So now we've talked about the variety of ways that you could use the service models. With respect to the dedicated services, it's still a challenge to determine what is the most popular service in the deployment, something that admins, we said, are always facing this challenge. How can I get around this? What tools can help? And we mentioned 2 tools. We're going to use this time to show you a demo of System Log Parser, looking at some logs and generating a report for you to see what information it can provide tackling this problem. So on our desktop here, we have an ArcGIS deployment. We're looking at the logs on the file system. We've downloaded system log parser, and we are running it. And we're going to point it to our deployment here using the ArcGIS Server file system browser. It can support a variety of log formats. We're going to take advantage of this one, and we're going to select our date range of time and our report, and click Analyze Logs. And so this is going through the file system, reading the data, and as you can see, it's a lot of log data. Hard to do by hand. That's why these utilities can really help provide this information in an easier digestible format than looking at the raw logs yourself. So the report has been generated. We can now look at the report. We'll go over some of the highlights. We'll start with the second worksheet here. And this is breaking down the requests, their popularity, and their performance. So by default, it's sorted by count. We can see that we have image service here, and it was requested quite a lot over the past 2 weeks. However, its average performance was pretty good. So in this case, I think it's fair to say that our SOC instance settings for this service is doesn't look to be a concern right away. So we'll continue looking. If we go over here to the side, we can sort by our sum percentage. And this is helpful information because this provides another perspective on how much time our deployment is spending. So while you can have requests for many services, how much time is being spent on them is also a key factor. So as we've sorted from a different column of data, we can see that this KML service is actually consuming a lot of time and resources from our system. So this is just a great way to take data and transform it into information. And as an administrator of a GIS deployment, I'd want to know this information. So we'll continue on looking at some of the other worksheets. We notice that we have wait time. So as we mentioned earlier, wait time is not our friend. We want to minimize that as much as we can. And we're looking at this here, and we can see that we have some services. Our image service waited about 14,000 instances worth requests had wait time in there, but they were fairly quick. However, if we just scan down a little more, we can see there was another service with wait time, and the average wait time was 3 seconds. So as an administrator, that's a concern. I want to increase my maximum to try to help bring that number down. And if you go down the column here, we can see there's a few more services that have times also for our consideration to increase that value. We'll go one more worksheet over to our instance creation time. Here we can see that we have right away very concerning information telling us that our California San Francisco service had a lot of requests with a very long startup time, 5 seconds. So that's 5 seconds our users had to wait. 1,000 requests, 1,000 user requests had to wait 5 seconds or more on average. That is a concern. As an administrator, I want to increase the minimum, or if I can, looking at some of these other candidates, which also have long wait times but not a very high number of requests, these would be fantastic candidates for the shared instance pool. So I can always ensure that these requests are serviced right away and minimize that wait time, minimize that startup cost. And with that, that will conclude the demo. We'll go back to our presentation. And so hopefully that presentation can help give you an idea of what some of the tools and utilities and information they can provide you when determining min and max values for your service instances. So web map tuning. Let's discuss this a bit. Ways you can tune your web map are through your hosted feature service. By default, hosted feature services are set to read-only, and this is a good thing. It makes them essentially faster. And the reason because they have less to do. When you have a hosted feature service that has editing enabled, that service has to preserve precision and resolution in case changes are made, right? It has to keep that data accuracy. But by making it read-only, it doesn't have to do that, right? It makes it smaller and faster. But there are situations where you do need to edit. You have a mixture of editors and viewers. And so in that case, you can use views, feature layer views. In this case, viewers still get the fast presentation of the data, and editors get the full data. Reducing clicks in your application. This is great, a great strategy, right? So your default extent can help reduce clicks if it is optimal and performs well, and definitely focuses on the area of interest that it should. So if I'm interested in Los Angeles, the default extent should put me in Los Angeles, and it should focus on where I believe the users are going to be able to just start working right away. If they have to zoom in or zoom out several times, those are extra hits against my deployment, which doesn't make sense. I only help myself by ensuring that this my first step is the best step. Cache tiles, where appropriate, use them. They can help reduce the amount of traffic, make the amount of dynamic requests to your system less. You can take this a step further. You can use cache tiles from ArcGIS Online. Then your deployment doesn't have to provide the bandwidth either, or the disk space. That's another benefit. Large amounts of feature services, feature service data can also be an issue. So, sometimes you can be asking for hundreds of thousands of points, and that it's just too hard to understand to the human eye, and it can hurt performance. So if you find you're in this boat, things that you can utilize are smart mapping, using the aggregate data like the heat map, and quantization. This is something relatively new, optimizes the geometry. This is a newer way of doing generalization. So it helps send less data back to your user, a lot less data. So this can be a great thing. So tuning a web map. So let's discuss how you can optimize your system to have your web map take advantage of it. So consider this scenario where you have a setup with one data set, publishes 3 services, which are then consumed under 3 web layers. So that's 3 services that have 3 ArcSoc settings that you have to adjust and tune, and each of them consume memory. And while it technically works, maybe there's a more optimal way. And let's discuss that. So this more efficient setup would be to consolidate layers. So we take our data source, we publish it as one service, and then we can use things like views to, or layer views to take advantage of this. And so we can have different views on our service, different takes on our service for our web map. But underneath the hood, they're all just using one service, which is great. Through the definition queries, for example, I can have a presentation of this data, and it appears like it's dedicated and it's very specific. But underneath the hood, we know there's just one service that we now have to manage and dedicate resources to, and it makes a more simpler setup which is always a good thing. Something to note that this is a strategy that may not fit if security is a requirement. Security is still done at the service level. So Portal for ArcGIS. So we had mentioned that there's not a lot of tuning with Portal, and that's true. Some things to note in the past was Active Directory. Active Directory with a lot of users in many groups had been an issue, but that's been greatly lessened with newer releases. Backups. I think that's probably one of the bigger things to keep in mind. A good starting point strategy for backups is the 1 to 6 model. One full backup to every 6 incremental backups. When you run your backups is also important. Running them off hours, not during peak business hours, as they can be resource intensive. Those are definitely good strategies. So your ArcGIS data stores. There's 3: your relational, your tile cache, and your spatiotemporal. Your relational, as we said, this is ArcGIS Server Manage, used for hosted feature services, runs Postgres. There is a good Esri white paper available on content management techniques that covers strategies that you can use. Worth a read. We recommend it. What it covers, the topics it covers, great for getting the most out of your deployment. Your tile cache runs CouchDB. This is used primarily for 3D scene layers in Portal. And we have then the spatiotemporal. This is the big data store used for things like GeoEvent, GeoAnalytics, ArcGIS Tracker. Ideal for high volume sets of data, large data sets. I think lastly here is the web adapter, and like some of the other components, not a lot to tune, but if there's one thing, some things we'd like to have you take with you is that the web adapters scale well out of the box. There's not a lot you can do, but log management can be a strategy that we would recommend. Logs for busy sites can grow quite large over time with default settings, and if it's available to try to roll over your logs to something like an hourly setting, it's more manageable this way, so you don't wind up with hundreds of gigabytes in one log file. If it's rotating every hour, it's a little more manageable. Easier to debug and view a log if it's just a few hundred megs or even tens of megs as opposed to the hundreds of gigs. And with that, I'll turn it over to Jeff, who will talk about system scaling.
Okay, thank you, Aaron. So system scaling, we're going to talk a little bit more about the IT infrastructure side. Aaron focused a lot on the software tuning level, different things you can do as an administrator and building maps and whatnot. These next sections are going to be more on the architecture and infrastructure side, because both pieces are important to building a tuned and scalable system. So with our IT infrastructure, there are multiple factors that can impact scaling, and some of these factors can be controlled, such as the server we deploy onto, whether that's a physical server or a virtual server. We might have different choices in the data center that we can choose, and choose the fastest processor type, for example. But there's other factors we can't control. For example, the network we happen to have in front of us, and whatever latency is there that we have to live with. And then storage, we have to take a look at that too, the different storage options, and make sure we don't have any bottlenecks at the storage level and storage is optimized. Next, please. So when we talk about scaling, there's two ways we can think of: scaling up and scaling out. Scaling up is where we take an existing machine and we increase resources to increase throughput for that machine. Examples are adding more CPUs, more memory, more disk, etc. Scaling out is where we add like machines as a unit of work to increase the capacity. So instead of one machine, we have 2, 3, 4, and so on machines, scaling horizontally. So both these strategies can be used together. We typically like to take a server, scale it up to a reasonable point, and then scale it out from there. So we don't typically want to make one server, a monster server, something reasonable, number of cores like those examples shown there, and then from there scale out. So for scaling up, a little more detail here. As I mentioned, we can't scale up forever. There are practical limits, and there's some other considerations as well. For example, you need at least 2 servers to support high availability. So even if you're purposely not necessarily trying to scale out, you'll still need to start with 2 just so that you have availability in case one fails. Large servers can lead to large capacity reduction if a server is unavailable. So if you only have 2 servers and you lose one of those servers for a while, you've lost 50% of your capacity. So if that is a major concern, and especially if that, it depends on that, how long that downtime can be, right? If it's a matter of minutes for, say, a VM to come back online, it may not be too huge of a risk or issue, but if there can be considerable downtime, you might want to look at spreading that out a little bit more, like across, say, 3 or 4 nodes, where in this example, with 4 nodes, if we lost a server, we would only lose 25% of our capacity. So some considerations there to think about. When we talk about scaling out Portal, we're somewhat limited. Portal by design is active-passive. And though you can deploy 2 portals in a highly available architecture, only one of those portals is active at any one time. But this isn't generally a concern since portal loads are light relative to service requests, and therefore a scale-up approach can be used when a portal server requires additional resources. So there's no issue with just taking that single server, or there's 2 of them, but it's active-passive, and scaling both of those up as needed by adding resources. When we get to ArcGIS Server, it's a little different story. We definitely can scale those out horizontally, building clusters as part of the site model. A typical scaled out larger site is in the 2 to 6 server range. 10 servers is probably a practical upper limit, but it's not necessarily a hard limit. We just don't usually see sites that go that large or beyond. Just from a practicality perspective. At that point, you probably want to build other sites and spread your services out. And there's certain server roles like raster analytics that do better with keeping the number of servers at a reasonable level, like to 5 to 6. And then some solutions like Geoanalytics server is very specific about how we support it with 1 and 3 server site configurations only. For data stores, when we scale those out, the relational data store is also primary standby, similar to Portal. So the relational data store is active-passive in nature, and therefore scaling out is not an option, and the server must be scaled up. As with Portal, this hasn't presented an issue since a 2 or 4 core server is typically adequate for most deployments, but you could scale it up from there further if needed. The spatial temporal big data store, however, can be scaled out as needed using odd number of nodes, example 3 or 5, and different sets of nodes within the cluster could be assigned specific sets of data, which the diagram there sort of illustrates. There are several workflows that require multiple node spatial temporal big data store deployments, such as those related to high volume event processing and using ArcGIS tracker functionality. It's highly recommended to use like at least a 3 node cluster for those. For the tile cache data store, since we're starting at 10.8, there are now a few options for scaling this data store out. And there are some pros and cons for each of the options. So the first one is a primary standby mode, but it's somewhat partially active because there's some read-only capabilities on the second node. And the pros here are drawing times are faster compared to cluster mode, which is that second option. And cons is it cannot scale beyond 2 machines. So that's something, if when you look at the types of loads you're going to be using, the number of users, if it's going to go beyond two nodes, we got to look at this other option, which is called cluster mode, where again we're using an odd number of servers in an active manner. You can add machines to meet storage needs, and if one machine is lost, cache data for each scene layer is available on one of the other machines. There are some trade-offs though, some cons, where query and draw times are slower. And this again is relative to the primary standby mode because scene layers have to query multiple machines. And also existing scene caches are not distributed automatically to recently added machines. So that might have to be rebalanced if you're adding, as you add another machine later. So I want to talk a little bit about architectures for the base deployment. Aaron talked about those base components earlier, the web adapter, portal, hosting server, and relational data store. So there's different ways we can deploy these components. And then from there, later on, we'll talk a little bit about building this out further with additional server roles. In this first example, all the components are installed onto a single server. It's illustrated by that white box with the yellow boxes representing the components. This is acceptable for small deployments, a handful of users, proof of concepts, and other instances where the portal and data store functions are limited and load is primarily associated with another function for which that portal is supporting, for example, raster analytics. So this is okay to start with and to do POCs and whatnot, but when we get into production, we'll want to look at a couple other options. One of those is a 2-tier deployment. This is where the hosting function is starting to get used, but the expected load on there is low to moderate. We're not supporting thousands of hosted services or we're doing a lot of analytics type work, but we are using that data store and those hosted services. For that kind of scenario, one scaling option is to deploy the hosting server and the data store together, separate from the portal server. This creates a web tier for the portal and an app tier for the remaining components. There are other options as well, but in addition to scaling, this option also aligns with architecture practices where we strive to keep components at the proper tier. For example, we don't typically want to put a data component at a web tier. And though the relational data store is a data tier component, it can be deployed with the hosting server as an exception to the rule because it is a sole client for it. That is, the hosting server is the sole client for the relational data store, and therefore can be treated as a single unit made up of those two components. For cases where the hosting function is really dominant in terms of increased loads, it is more appropriate to separate the relational data store onto its own server to allow for more control over capacity and scalability. Each of the servers can be scaled up as needed based on the specific workloads being supported. And we're seeing more and more architectures align with this pattern because of the increased use of ArcGIS Enterprise and related capabilities. There's more and more use of that data store in the hosting server, so these 3-tier deployments are becoming more common. And finally, when we think about high availability, when that's required, the architecture includes various scaling options, a little bit of scaling out and scaling up as previously discussed. So at the portal level, again, we have active, passive, 2 portals. The GIS server tier, minimum of 2 servers, but we can scale that up and out as needed. And the data store, which is active passive, but we can scale those servers up as needed. Further, with the presented conceptual architectures we've been looking at here, the web adapters have always been shown hosted alongside the portal as part of that web tier. But often in architecture designs, the web adapters are placed onto a separate consolidated web tier, separate from the portal. There are reasons why we would not do this, or why we would have a dedicated web tier. It's sort of outside of the scope of this tuning presentation, but it's worth mentioning so that it's not assumed that the web adapters should always be co-hosted with the portal. And as Aaron mentioned, that's a very light component, so we definitely have options where we can place that in terms of not worrying too much about the load itself. Okay. To expand these topics, let's talk about workload separation a little bit. So as mentioned, we start with that base ArcGIS Enterprise deployment as our foundation and then build upon it. This begins with identifying the various server roles needed to support the desired functionality while employing what we call workload separation to ensure we are building a scalable architecture. That is, it would not be a good practice to deploy a GIS server and run our mapping, geoprocessing, image, and other types of services all on that single server. We want to separate those out onto specific servers and sites, and that's at the heart of workload separation. And workload separation is a design approach that aligns the technical implementation with your organization's business requirements as they relate to data management, analysis, and visualization. So those are sort of like categories that we use to help define how we divide these things up and create different sites to align with workload separation. And when we do this, when we take this approach, we're essentially doing this to maximize system performance, reduce the risk of service interruption, improve the ability to monitor independent deployments, and in some cases align with licensing requirements or constraints. So in alignment with workload separation approach, we need to identify which server roles are required and where it makes sense to separate those functions onto their own GIS server sites. This is a bit of a judgment call for the architect, but assuming there will be adequate workflows and user loads to justify their approach, we can start by separating GIS servers by licensing roles. That is, we typically desire to separate image services from map services, and also from heavy processing such as geoprocessing. There are other licensing roles such as GeoEvent server and GeoAnalytics server, which, because of their uniqueness, should be deployed onto separate servers as well. So an example here, architecture, using workload separation to build on the base deployment, we can see how this starts to look for an actual deployment. In this example, hosted, map, utility network, and image services have been deployed onto their own GIS server sites. This architecture is also built with high availability in mind, therefore each GIS server site is scaled with 2 servers at a minimum. This architecture also has a distinct web tier where we have deployed all of the web adapters. Another larger example, kind of more at the extreme end, where we continue to demonstrate how workload separation can allow us to effectively manage these large deployments and divide the load up. In this large example, there are a total of 10 GIS server sites performing various functions in addition to the hosting site, which is part of that base deployment in the upper left corner. So here we have a mix of hosting sites, imagery site, multiple viewer sites, geoprocessing, some third-party application sites, and so on. And so you can start to really see the value of workload separation. And try to imagine if all this was condensed to 1, 2, or 3 sites, it would be much more difficult to manage, troubleshoot. And if something goes down, it would have a much bigger impact across multiple applications. So with that, that concludes our presentation, and we thank you very much.